this is still part of 6-7. So we've been kind of dragging this out, but it's worth dragging out because it's complicated stuff. And this is the application part of the sine and the cosine. So we're focusing solely on sine and cosine curves for this. All right, here's what I want you to do. The very first thing we do is we have to figure out what are the points associated with high tide and low tide for this problem. So we've got low tide at 2 meters, and the first low tide is occurring at 9:18 a.m. Now, all of this is in reference to midnight. So from midnight is where we're obviously thinking about our time. So what's going to be funky about this is we don't have theta as our x-axis anymore. We actually now have time. But it's still going to model as a sine or a cosine curve. So the low tide, for our low tide, we've got the following points. We've got distance, which is actually time, is 9:18. Now, what we have to do is we're going to convert these minutes into decimal hours. So how do I make 18 minutes become hours? Anyone know? Divided by 60. That's what we did. So we did that. 18 divided by 60, and I get 9.3. That's time. And then y-axis is the height of the tide, and we said it's 2. So there's our very first point that we're going to plot on this graph that we're going to use to be able to draw our curve. In the high tide, is occurring at 3 a.m. and it has a value of 14. Okay, so these two become the first points that I plot on my graph. So here's my graph. And again, this really shouldn't say x, it's time. And this is not y, but it is height as a function of time. So we're back into function notation. All right, so let's plot these 2 points. Let's start. Which one comes first from midnight? Low tide or high tide? We'll look at the numbers. Which one's going to come first? High tide is. 3 a.m. is before 9.3 a.m. Right, so 3 a.m. We're going to go high tide. We're going to count over. So this 0 right here, that represents midnight. And we're going to go over 3 and up 14. So over 3, up 14, and I get a point right there. 3:14. One more. There we go. 3:14. There's my very first point on my curve. I think I'm going to shave the head again this week. Yeah, too much hair. Too much hair. My underside is too involved. Corbin ends. All right. The next point. 9.3, bless you, 2. So we're going to go out to 9.3, and we're going to have to estimate this one, and then 2. So that's about right there. 9.3 and 2. Okay, now that right there, that little point-to-point representation is high tide to low tide. So get your thinking caps on. Which trig function would start at a high tide? Oh, cosine would. Yeah, cosine would. Very good. So let's draw what we have right here. Is this a full cosine when I just go from here to here? How much of a cosine is that? You guys are on it. That's half of a cosine right there. We talked about yesterday, from high tide to low tide, max to min represents half of a period. Half. So here's my curve. Oh, beautiful. Nice looking curve, but it's only half what we need. And then what's going to do? What do you mean out first? Yeah. So we talked about this yesterday. Jordan and I had a little conversation about your curve drawing. Yeah, it doesn't go straight line. It has this little drop, like a roller coaster. Little roller coaster drop and then comes in. All right? Nice sound effects. Okay, now, so we know it's a cosine curve. Next thing I need to do is figure out what's the period of this cosine curve. So can somebody tell me why I need to know the period? Okay, that is true. To make the other side, that would be true. But what's the more... There's a piece of my equation that I cannot find unless I have a period. No. It's B. I can't write B until I know period. Just don't vomit at the mouth with everything. I mean, vomiting at the mouth is usually where you vomit. You get an idea? All right. I know. All right, so we need period so that I can find B. And this distance right here, from that point to this point, we said is half of a period. So I'm just going to use that right now, and we're going to go find B. All right, but we got to find, let's see, half of a period is equal to a max value minus a min value. These are the x coordinates here. So I'm going to say that half of t is equal to, well, here, why don't we do this? Why don't we just say p, not t, is equal to twice this difference. So this is how you can always find period if you know the max and min values. These are not the y parts of max and min. These are the x parts of max. So this, we're talking time. So I get this. 2 times, let's see, we're going to go from 9.3. So this is really min minus at max, just because I'm doing my larger number first. 9.3 hours minus 3 a.m. hours. So we're switching these.
Can you do that?
Yeah. You can do that. I just don't want to. I don't want a negative number. Period is always positive. And I get 2 times 6.3. So we have 12.6 hours is the period that it'll take for this high tide to get back to high tide. So at 3 a.m. it's high tide. 12.6 hours. What would the time be, by the way, from 3 a.m. to 12.6 hours later? What is that?
Yeah,
3 and then a little something more, right? 0.6 hours. We'll put it back in a minute. So yeah, it's going to be 3 something p.m. before I get back to high tide. So let's go plot that other point. The next high tide would equal 3 plus 12.6 or 15.6 hours, which is really 3.6 hours.
Wait, is the next one?
This is the next high tide. Because a point on a curve and its corresponding point a period later takes me full cycle. So I'm going to go to 15.6. That's about right there. And there I am back at high tide. So here's the other part of my curve. So there's representing a full cycle of high tide to high tide. Yeah.
How do you know, I mean, when would you know if it's like max and min of the x value?
Okay, good question. Good question. These are always going to be of the x values. Every time.
Wait, that is 3.6, right?
3.6 hours, meaning 3 p.m. I'm just converting it into, so 0.6 hours, take that, multiply it by 60, and you get 36 minutes. So this is the same thing as 3 hours and 36 minutes. So 3:36 p.m. in the afternoon is when I'm going to have high tide. Okay? So we can just leave it as a decimal hour because that's what we're plotting on our axis.
Okay.
Sam,
What were the coordinates for that last for the end?
for this point over here, 15.6, 40. And we got that because we added 12.6 from 3 to get back to high tide. Okay, how are we doing so far? Following this, or are we lost? Yes. max of x, min of x. So you're only talking about the x coordinates of these points to find period. Period is related to this, not this. Okay. All right, so we have now found t, which means from t, what could we find? B. So we're going to go, since we have it, let's just go find b. So we're going to use this. What's my equation? How do I find b once I know what t is? 2 pi over t. 2 pi over t. So we're going to go 2 pi over 12.6. And we're just going to have to convert it to a decimal number. So somebody punch that in here. What's 2 times 6.28 divided by 12.6? 0.52. Is that right? Is that right?
0.498.
Oh, okay. 0.498. So 0.498. There's our b value. All right. Got one of the parts for my equation. Okay, now what do we do? So we drew our sketch. We physically see it is a cosine curve. And if we're going to use this as the starting point, the next question might be, do I have a phase shift?
Yes.
Have I started somewhere other than the vertical axis?
Yes.
Yes. If you start at a point to the right or to the left of an axis vertical axis, you have a phase shift. So this distance from here to here, that's my c value. So what is my c going to be? Minus 3. In my equation, it's going to be something minus 3 because I've gone to the right. So right now what we're going to do is we're going to write it just as c is equal to 3. 3 to the right is what we're going to say. C is equal 3 to the right. And what we know is that 3 to the right really means t minus 3. That's really what it means. All right, good deal. So now we have B and C. We're halfway there. We need A and D. How do we find A? It would sure be nice if I had some. I wonder if I have any formulas for finding A. Oh! Oh, look at that. Max minus a min over a 2. Okay, now here, remember amplitude is dealing with y values of max and min, where period dealt with x values of max and min. So let's go and look at our coordinates again. So our coordinates are 9.3, 2 and 3, 14. So we're going to do 14 minus 2 as my max minus min. And divided by 2, and I get 12 divided by 2 is a 6. There is my A. Now this is just beautiful. We've got B, got C, now have A. Now we've got to go find B. I would sure be nice if I had the formula for finding B. Max plus min divided by 2. All right, so now we got 14 plus 2 over 2. Which means D is equal to 8. Man, that's a lot of hard work. You're burning some calories here. Yes, Bobby. Okay, good question. It has to do with the formulas that you're supposed to have memorized. Okay, so an amplitude is this part of a curve. Is this y or x? I know you do, probably 12 times. And then This part is x, and that deals with period. So that's why max minus min for period is x values. Max minus min for amplitude is y values. All right? That's okay? All right. Now, do I have all of the pieces to be able to write the equation of this tide problem? I do. I see the graph. There it is, one period of the graph. That's okay. We got one period. It's good. I have enough information to write my equation. So if I do this right, what should it look like? What should my equation be? There's everything there for you. Tell me what it should be. Y equals 6 cosine. Okay, that's where it goes a little fuzzy. So here's what I recommend doing. Keep the b separate from the t minus 3 part. So what I mean by that, write it like this. So we know it's going to take on y equals 6 cosine. Now the b, here's what I want you to do. I want you to just put the b value right afterwards. And then I want you to put the parentheses for the x, or in this case, t minus c part. So t minus 3. And then what? Plus 8. That should be the equation for this thing. Now, there is another way to write it with distributing the 0.498 in. You don't have to do that. Here's, let's see, does it look like the one we have? Oh, look at that. Isn't that amazing? That is amazing. Let's see if it looks the same. Oh, my goodness. It even looks the same. Why am I stressing me out? Yeah, he was stressing me out. All right? So, were there a lot of steps involved in that process?
Yes.
Yeah. Was it hard? Probably because it was the first time we did it. But this is what we're going to do when we model. We draw a little diagram of what's going on. The diagram helps you come up with a graph. The graph helps you come up with my parts. All right, what am I doing? Scrolling down? Okay, where am I going? Right there? On fire, right? All right. Any questions on this one? Can we roll to the next one? See how many we can get through. Probably just one more. All right, how about this? Oh my God. How about if this YouTube, you just go look at the YouTube and write it down for you. That work? Okay. If you want to write it down, go ahead. Write down this generic information. Spring, 36 inches off the floor. Draw a little diagram, might be faster than writing it down. So we've got a floor, and then 36 inches above the floor is this spring that has a weight attached to it. And right now, the weight and the spring are just sitting there. They are in their non-loaded state. They haven't loaded the spring in the sense that they haven't pulled it down. I am. Okay. We can talk about it. Okay. So I've got that spring, and I've got it hanging out 36 inches above the floor. And then what I'm going to do is I'm going to pull that spring down 7 inches from where it currently is. So now how high above the floor is it? It's 36 minus 7. It was at 36 that I pulled it down. So now it's only 29 inches up. And I let it go. What do you think a spring's going to do if I let it go? It's going to go up, and it's going to go down. So if you guys have been in physics at all, you know that when I pull the springs down, I've loaded the spring with what's called potential energy. You know what? So you do that already? So I've loaded the spring with potential energy, which means when I let it go, that energy is going to release and become a different kind of energy, because movement energy is called kinetic energy. So the spring's going to go, and it's going to go up, and is it going to stop at 36? No. Where's it going to go? How far above 36? Another 7 inches. Because we started 7, I loaded it with 7 additional inches of energy. It's going to go to 36 and 7 more. Now in the real world, it's not going to do that forever. It's not going to oscillate back and forth because of friction. It has what's called dampening. That spring is going to dampen and eventually it will come back to rest. In a situation where there is no friction, that spring would forever oscillate back and forth between 29 and 43. 29 and 43. And so what we do is we model for a very, very short period of time this spring movement. And then that's how we come up with our equation that we use. Yes?
So in space, would it
Good question. In space, would it continue infinitely? The problem in space is not so much the fact that there's no air, it's the spring itself has friction. Yeah.
so
Good question, though. All right, so does everyone understand what's happening? Got a visual in your head? Okay, now notice how long it took to do this. Once we pulled the spring down and we let it go, it got to its maximum height 0.75 seconds after we let it go. All right, so all of this information right here, that one, and the one I just underlined, is going to help me draw my diagram. So let's do that first. Let's draw the diagram. Everyone got those numbers in their head? That's right, sister. Funny of that. Thank you. Thank you, my lady. All right. So let's draw our at time equals 0, there's time. Again, height is a function of time. So in this graph, do we have a phase shift? Where is 0, by the way? Where's 0 time? My hand is on the spring. Where is my hand on the spring in terms of time 0? Is it at 36 inches? Is it at 29 inches? Where is it?
29. 29. Always 29.
What is time measuring? Let's talk about that first. What's time measuring?
That it starts.
What?
From the point that it starts.
From the point that it starts oscillating. Right? So am I oscillating? Is it just the spring moving if it's just hanging at 36? It's not going to start moving until I pull it down to 29. And it's at that point, at time 0, I let it go. And it goes. So time 0, right there, what's the height of the spring above the floor? 29. The height of the spring above the floor is 29. So we're going to go up here, and we're going to put our point in. 0, 29. That's our very first beginning of this spring. And then we let it go, and it does its thing, and it says that after 0.75 seconds, it reaches its maximum value. So we're going to go 0.75 seconds and go up to 43, and we're right about there.
How would we get 29 from?
It's not on here. It's figured out from here. Can you figure out where I got 29 from based on the information right there?
Between.
No, look at the information and look what I did to the spring. Where did it start? Where did it start? Above the floor. Then what did I do to it? If I pull it down 7 inches from 36, how high is it above the floor now? That's where the 29 is coming from.
Well, no, everything 29.
All right, so look at the curve. There's the curve. What kind of a function is it?
Sine.
No. A negative cosine. Why is it a negative cosine? Okay. Because this is a cosine curve. It started at its minimum value and it went up to its maximum. Even though sines start at a point and go up, they don't start at their minimum. They start at their axis. So this is a minimum point to a maximum point. It is a negative cosine curve. So there's my sketch. And then I would repeat this. What's the period of this graph? How long take to get back down? 1.5 from what? From 0. So it's a total of 1.5 seconds. Okay, you got to remember this, people. This will make or break your problem. Max to min is always half your period. So if it took us 0.75 seconds to get to the max from the minimum, it's going to take us another 0.75 seconds to go back down to the minimum. So I'm going to finally get out here. 1.5 seconds, back at 29. And the curve would then come back down to its minimum. So there's our spring action. So there's part A, graphing it. And now we go find all of the parts here. So find the amplitude, the period, the axis of the function. Again, that's your A, your T, which helps you find B, and then the D part of this is what that's asking us for. So let's go do that. Let's talk about period first. We just said the period is equal to 2 times maximum x value, in this case, minus minimum x value. We go 2 times 0.75 minus 0, or 1.5 seconds. There's the time it takes to go through a full cycle. And then from this, find B. 2 pi over 1.5. Somebody give me a decimal number for that, please. 6.28 divided by 1.5. .08? 4.08. Oh, 18. 4.18. Okay, there's my B. Let's go find A. How am I going to find A? What am I going to do? Max minus min divided by 2. Max minus min. All right, somebody have this number for me? It's 7. How do I know it's 7? Because that's how long, that's how far I pulled the spring down from where it stopped, where it was just lying before it loaded. Pulled it down 7, that's got to be the end. Why is that not? I don't know why that's not. And then D.
Wouldn't A be like -7?
The atom. Okay, now let's think about this because this is just intuition. You guys done? Thanks. Intuition here. Where's the axis of the spring? 36. Why is it 36? It's the midpoint, but more importantly, it's 36 because that spring was doing how high it was above the floor before I pulled it down. That's where it just hangs out without doing anything to it. So 36 becomes my axis point, and that's an equation now. So y, or in this case, h of t equals 36 is the equation I would have for my axis. If I ask you for an equation for axis, you got to say y equals, or in this case, because we're talking about height, h of t equals 36. All right, I have everything I need. There's part B, and then finally we write the equation. No phase shift because I start on the axis. So my equation should be h of t is equal to a times, now this is a negative cosine, so we're going to stick a negative out in front of that 7. Start it as a minimum. And then we're going to go ahead and separate our b and our t minus plus thing going on, although we don't have that phase shift. So my b is a 4.18 times t, no phase shift, so I can just close that up. And then plus my d, because I'm 36 inches above the floor. It's not that hard, it really isn't.
that's big.
And 36 is
Yeah.
just like,